In Module 6, we're going to be covering Chapter 6 in our textbook, which talks about viscous flow in pipes. Now, viscous flow in pipes is seen all around the world and is used very, very extensively. So it is important for us as engineers to be able to understand these specific applications, such as viscous flow in pipes. It's an important practical flow because it's used everywhere to transport air, to transport water, to transport gasoline through pipelines. It's a very, very important flow to know. And using our knowledge from the previous modules, we are now able to study this more specific application and see how the engineers in the past came up with solutions to solve for piping problems, essentially. Okay, so we know that there are no exact solutions to the Navier-Stokes equations, and a differential approach doesn't really yield an exact solution. So we have to somehow estimate this solution to come up with a good engineering solution for the problem. And this comes by essentially looking at all three methodologies, looking at a control volume approach, looking at Bernoulli approach and a more differential approach, and also looking at experimental data to understand our flow. And we're going to be looking at different types of flows as well in pipes. So there's going to be laminar flow and turbulent flow, and seeing how we can solve problems for each of these problems. So in this video, we're going to be focusing on the first part of the chapter, and then in our live lecture next week, we will be focusing on turbulent flow more specifically. So let's look at how viscous flow in pipes works, and we're going to start with what type of problem are engineers faced with. So what is a basic pipe problem we would have to solve? So a basic pipe problem that we would have would be, we are given, for example, a pipe geometry, and from this pipe geometry, we want to figure out the desired flow rate and fluid properties. So what flow rate do we want, and what properties do we want to use for our fluid? So let's say we want to transport through a pipe, we want to transport some crude oil, for example. So we know what the fluid properties are, and we say that we want to have, let's say, 1,000 meters cubed per second of oil going through. So now we have a definition of our problem. And in order to solve for the problem, we're going to have to figure out the two following things. So we're going to have to figure out what pressure drop is needed to drive the flow. So remember that flow is always created by a force, and this force is usually created by a pressure drop. So if we have a high pressure on one side and a low pressure on the other side, the flow will start driving from the high to the low pressure. Okay, so we can figure out from our theory what pressure drop we would need to drive the flow. And in a second instance, we're also going to answer the question, what flow rate can we achieve? If we don't get enough flow rate, we need to go back to the drawing board and probably add some more pressure, or change the piping so that there's less friction, or do some sort of design iteration. But this is a typical example of a piping problem that you would be faced with. And your example problems, as well as your study problems will follow this kind of procedure. So one thing that we're going to look at in pipe flows is that we're going to assume that all of the pipe flows that we solve for in this chapter essentially are going to be all incompressible flow. And this is usually the case in pipe flow because we don't deal with extremely high velocities. And if we do transfer any gases through pipes, we usually don't have compressible effects. However, in some specific instances, you could have compressible flow, but in this chapter, we're going to focus on pretty much all incompressible flow. So the first thing we want to talk about is following Module 5, we want to talk a little bit more about Reynolds number and what it means in the context of pipes, essentially. So we're going to look at Reynolds number, and this is section 6.1 in your textbook, just to locate you in the textbook. We're going to talk about Reynolds number regime. And we know that for a flow, we don't have a general solution for pipe flow. So we have no general solution for pipe flow, so we can't just say, apply this equation to pipe flow and you'll know all the answers that you have. It's just one equation, you plug it in, and everything is okay. Flow in pipes actually changes drastically as Reynolds number goes up. So we can say that the behavior of the flow changes drastically as Reynolds goes up. And we're going to put RED, so Reynolds with a sub D. And this little d here is for the diameter of the pipe. And for pipes, we always use RE sub D, okay, just so you know. In other instances, in the later modules in this class, in the following modules, we're going to be talking about Reynolds X or Reynolds L, because we're going to be looking at the length of a plate, for example, okay? But in this case, we're only talking about tube, and inside a pipe, we have Reynolds dependent on the diameter of the pipe. Okay, so we can say that because this behavior changes, essentially what we have is as Reynolds goes up, so if Reynolds goes up, what happens is our flow ceases to be smooth, and in our class we call smooth laminar, and becomes turbulent. And we'll look at the different types of things that can influence Reynolds number and why we would have turbulent flow versus laminar flow. Okay, so we can also say that the phase that occurs between laminar and turbulent is called a transition phase. Okay, so we essentially have laminar flow, we have transition flow, and we have fully turbulent flow. Okay, and we can say, very important, that Reynolds number for flow in a circular pipe is accepted to be transitioning at Reynolds equals 2,300. So RED is equal to 2,300 is, and this is for flow in a circular pipe, so it's not applicable to any other type of system. Is accepted to be transitioning. Okay, and this is also called the Reynolds number critical. Okay, so they also call it critical, where we have this switch from essentially a very laminar flow to a switch that is now transitioning and then eventually becomes fully developed if we have a higher Reynolds number. So this is very important. This is a very important number. Okay, this means that if we know that our Reynolds number in our flow is equal to 1,000, we're going to have laminar flow. If we know that our Reynolds number is equal to 5,000, then we have turbulent flow, for example. Okay, so we're going to do a really quick little example. So just before we move on, we know that the equation for Reynolds number is rho times velocity times diameter over mu. Okay, so we have density times velocity times the diameter of the pipe over mu, which is our viscosity. Okay, so all these different terms can affect Reynolds number. Okay, and we know in a pipe, because Reynolds number is dimensionless, we know that if the Reynolds number is equal to 2,300, no matter the liquid we use, we're going to have a transition phase occurring. So let's do a very quick example of what would happen and try to see at what velocity would transition occur in water and air at 20 degrees. So let me write the question. For flow at 20 degrees Celsius in a 5 centimeters pipe, so that would be 5 centimeter diameter, at what velocity would transition occur? So how would we solve this? Well, for air, we could just solve it by saying the Reynolds D we know is equal to 2,300, and we know that the equation is equal to rho times velocity times diameter over mu. So we can plug in all the values that we know. So if you go to your appendix, I'm not going to go to the appendix now, but if you go to your appendix, you would have 1.205 times velocity times 0.05 for your diameter over 1.8 times 10 to the minus 5. And you know that this is equal to 2,300. So if you rearrange this, you find that the velocity is equal to 0.7 meters per second. So the velocity is actually pretty low. So the velocity would have to be even lower for us to have laminar flow. So with air, it's, let's say, very unlikely that we have laminar flow in a pipe, except if the flow is very, very slow. Now, if we look at water and we repeat the same procedure, we have 998 times V times 0.05 divided by 0.001. Okay, that's our values for density and viscosity and our diameter once again. And we know that this is equal to 2,300. Therefore, our velocity for water for transition would be equal to 0.046 meters per second. So again, extremely unlikely that you'll have laminar flow with water as well. Okay, in a 5 centimeter pipe. If we increase the size of the pipe, then we would get an even lower velocity. Okay, so it really depends on the size of your pipe as well. But if you plug in the numbers for your size of your pipe and you change the size of the pipe, you can see how it will affect velocity. So you can do that as a little exercise just to see what the velocity would look like if you change parameters or you change some things. So what we can conclude from this is that we have very low velocity in both cases. And what this means is that most air and water flows will be turbulent. And so that means that we really want to try and figure out a solution for our turbulent flow. So we want to try and figure out a solution for a turbulent flow. But in order to understand the turbulent flow, we're going to go through and solve for laminar flow first, and then look into turbulent flow. Okay, so here's an example of what laminar flow would look like with a high viscosity, low Reynolds number laminar flow coming out of a pipe. So you see you have two nice smooth streams of water coming down and coming out, and you can see that the flow is very smooth. It's very laminar. Whereas you have another example here where you have low viscosity, high Reynolds number, and you can see that you have some turbulence here. So you have some different shapes, and you have a lot of different directions in your jet, essentially, in the flow coming out of that pipe. Okay, so that's an example of what laminar and turbulent flow would look like in actual real life. Okay, if we go even further with this, we can also look at another figure, which I'm going to copy over right now. And I'm going to copy over two things, just one at a time. Sorry about that. And discuss them right after. So the first handout that we have here is a little bit more of formation of what is called puff flow in a tube, essentially. And we can see what's happening near the entrance, somewhat downstream, and far downstream, essentially. So you can see that in this first section here in A, from here to here, we have flow coming in, and it's pretty organized flow, but we start having these waves moving up and just sort of increasing the turbulence of the flow. So we actually can call this our transition region. So the first region on the left, we can call transition. And then we reach a point where we start getting more and more turbulent flow. So in this section here, we have turbulent flow. So we can say that this part is called turbulent. And moving forward, we seem to keep having these turbulence bands, like a lot of turbulence here, and we can see that it's not very organized as a flow. Okay, now if we look at it more from a zoomed out point of view, we can see that we once again have, in our second instance, we have transition is occurring in a much smaller window, and then eventually we have turbulent flow. And you can see that somewhat downstream you still have this turbulent flow, but it actually starts organizing a little bit more. But you can see that essentially what we can conclude from this is that turbulent flow seems very, very chaotic. Okay, it's very hard to determine what's happening and how it's working, especially in this transition region here where it keeps on changing. Okay, we don't have a clear understanding of what's happening there. Now, if we look at far downstream and more downstream in our flow, we now get a flow that is a little bit more organized within our system, and this looks more like we can describe it as fully developed, or we can call it like fully turbulent as well. Okay, we have a more fully developed flow and we understand what's happening a little bit better. So at Reynolds of 2,300, we can say that intense turbulence is happening because of this transition, and we call them puffs. So transition, we can also call them puffs of intense turbulence at transition. And we can categorize our flow in different steps. And I copied over the diagram just so it's easier to follow and it's easier to have all the information there. But essentially from 0 to 1 for Reynolds, you have highly viscous laminar creeping motion. This would be like honey moving in a jar, very, very slow. Then 1 to 100, we have laminar flow, strong Reynolds number dependence. So it's very important to know your Reynolds number because the flow is going to change a lot based on the Reynolds number. Okay, you're going to go from creeping motion to more of a regular, very slow water motion, very organized water motion, for example. Then from 100 to 1000, you're going to get something called boundary layer theory. And we'll look at boundary layer theory later. But essentially, boundary layer theory is the fact that a boundary layer is now forming on the walls, and we get this layer of flow that is sort of organized, but creating this boundary where we have lower velocity at the outsides and higher velocity in the middle. Okay, then from 1000 to 10,000, we have transition. So you can see that if you have Reynolds of 2,299, it doesn't mean you have laminar flow. Okay, the Reynolds number is approximately a value at which transition is known to occur. This critical flow is known to start occurring around 2,300, but it could be occurring at 2,000 or at 1,500 or at 5,000. It's not a precise science. It's again from the randomness of the flow, what happens. There's a lot of different things that can happen that create this transition to turbulence. Then from 10 to the 4 to 10 to the 6, we have fully turbulent flow. And we still have Reynolds number dependence, so the flow will change as the flow shape and the flow pattern will change as the Reynolds number goes up. And then once we get to over 10 to the 6, we have fully turbulent flow, and the Reynolds number doesn't really matter above that. We just know that we have fully turbulent flow, and we know it's 100% turbulent, and it's sort of organized turbulent and doesn't really change with speed of the flow or anything like that. Now, which regions are we interested in for our study? Well, we're interested in really two regions. And one of the regions that we're not interested in, because it's very hard to gauge what is happening, is our transition region, right? In our transition region, it's extremely hard for us to predict what the flow is going to be doing. So we actually are interested in more of, one is a laminar region, and the other one is our turbulent region. And we'll add here that we want fully turbulent region. And the reason why we're interested in those two is because if you have, for example, a pipe that's very long, let's say it's 10 miles long, we're going to have turbulent flow within a 10 miles long pipe usually. So we're only interested in the turbulent flow. Even if at the entrance of the pipe we might have some transition from laminar to turbulent, it doesn't really have much of an effect on the whole flow of our pipe. We're also interested in laminar for shorter flows in smaller pipes. Okay, if we have a very small pipe with flow moving very slowly, we are then maybe interested in laminar flow as well. But the transition flow, since it's so hard to understand, and it's actually a transition usually from laminar to turbulent within a pipe, we're not going to bother too much with that. Although we are going to try and study whether or not we are laminar or turbulent. So we actually have to figure out if we're laminar or turbulent. In order to do so, you're just going to solve for the Reynolds number, And if the Reynolds number tells you you're at 100, then you know you're laminar. If the Reynolds number tells you you're at 20,000, then you know you're turbulent. And you can solve the problem in a laminar way or a turbulent way. So we're going to develop solutions in both ways, essentially. So in just to give you a little bit of history, in 1883, Reynolds found out this. So Osborne Reynolds, who was a physicist, found out that Reynolds diameter would be equal to 2,300 for our critical region, which is our transition for pipe flow. Just to give you an idea of how. And what he did was he actually did some pipe flow experiments with dye in a glass tube. So he would inject a dye in a glass tube and would look at how his flow would essentially develop over time to have a laminar flow, a turbulent flow, and looking at the difference between the two essentially. And what he came up with, and these are not the pictures from the experiment, but the pictures from just recreated for the textbook. But what came out was that we have this shape right here. And this is pretty self-explanatory, but it shows you how flow coming into a pipe initially is always laminar. Okay, we see that the flow through a pipe in the initial phase of all three is initially laminar, and as you move forward, the formation of this dye now creates this turbulence region. And B is a high speed turbulent flow, and C is just the same as B. It's just a spark photograph. So a spark photograph is just a photograph in time of what's happening, and you're able to to find shapes for the turbulent flow. Now, Reynolds number can be written in two ways. So we can say that Reynolds number, and I'll put the sub D because we're going to use sub D in this chapter. Reynolds number is rho times V times D over mu, like we said. But we can also write it as V times D over nu, Nu, okay? And this is a different term called the kinematic viscosity. And what the kinematic viscosity is equal to is just mu over density. So it just takes density into account. So this is usually called the dynamic viscosity, and this is usually called the kinematic viscosity. So just two different ways of writing viscosity, but if in your book you're given, or in a question you're told the kinematic viscosity is this much, you can use a kinematic version of the problem. Okay, you can also find the kinematic viscosity in your tables in your appendix of your book, but you can also find dynamic, either or. You can find both. Okay, so moving forward from this, we see that since there is a transition from, so we can see in the first part, in part A, we have low speed laminar flow and the flow stays laminar throughout. Now in part B and C, we see that we actually get some turbulent flow and some transition. And we need to understand why it's transitioning. Okay, why is this happening? Well, the reason it's happening is because we have walls in our flow. So we can say that internal flow is constrained by bounding walls and viscosity effects grow and meet through the flow. So the effects of viscosity and the shear stress in our flow increases as we go further into our flow. Okay, so we go further from left to right. And these effects eventually meet through the flow. So we'll look at what that looks like, but now we're just writing the description. So try to think of what this would look like, but essentially we're going to copy over another diagram from your handout and describe this diagram next. So we have this statement that we said that internal flow is constrained by bounding walls. So we know that the walls are going to be constraining to our flow, and the viscosity effects grow and meet through the flow. Okay, so if we look at the flow at the entrance of a pipe, for example, we have this type of, so we're looking at the flow here coming into a pipe. We have this compression of flow, but the flow is coming in without any compression at all and without any restrictions at all of walls. So initially, when we come into our flow inside our pipe, our velocity pretty much looks like a 1D profile of velocity. So initially, we pretty much have what would look like a 1D profile of velocity. And let me just erase this first arrow. So we have like a 1D profile of velocity with slightly lower velocity, possibly at the exits, due to the fact that we have this boundary layer starting to form on the entrance region. Here we have a little bit of a start of like separation of flow due to the walls here. And what we can say is that this first part of our flow is called the developing profile region. So a profile is essentially developing at the start of our flow. So as you go further and further into your system, your velocity at the edges is going to go down more and more and more, because the viscosity effects are going to be felt from the walls. The walls are going to start slowing down the flow on the outside, which is going to slow down the next layer of flow. So if you think of your flow having different layers, essentially this layer here, so this arrow here, is going to slow down the next arrow, which is going to slow down the next arrow, etc., 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 as you go through the flow. And this is also called the flow that is inviscid for now. So as you come into a flow, initially you have an inviscid part which is not felt by viscosity. It takes some time and some distance to figure out essentially that the viscosity is all throughout the flow essentially. Okay, and this entrance region is called LE. And as you can see, the pressure drops linearly. The pressure drops initially. So you can see that the pressure in our flow drops initially, not linearly, but after we pass LE, we have a linear pressure drop in our fully developed region. So the pressure drops as we go further and further down the region. And that makes sense. We're going from high pressure to low pressure, and that's why our flow is going from left to right. Okay, so it's at a certain point after the entrance, so after this entrance right here, we have a point where our boundary layers merge. So both of our boundary layers from the top and from the bottom eventually merge to the middle. And a little bit of a distance after this, we can call this point here, this new line here, we can call it our fully developed region. So we can call it our fully developed flow region starting at this point. That means that further down the line, our flow is not going to change anymore. And we also know that after the fully developed region is reached, our velocity is now a function that we can develop very easily, and we can come up with an equation for this arc of velocity to find the velocity as we go along our line. So we can say that in the fully developed region, we can say that our u, which is going to be our velocity, is going to be a function of r. Okay, so u is just a function of r. The velocity profile, okay, it's written here too. The velocity profile can be determined by just a function of this radius. So depending where you are on the radius, you will be able to find your velocity. Okay, now in the region before that, in the entrance length or the developing region, so before LE, we can say, before the length of entrance has been achieved, we know that our velocity u is a function of r and x. Okay, as you go further and further down the line, your shape of your velocity is changing. Your shape of your profile is changing until it reaches a constant shape in the fully developed flow region. Okay, so that's very important to understand. So hopefully that makes sense. If you need more, if you need more clarification on this, just go to your book. Your book has a pretty good description of this graph as well. Okay, but this should be pretty clear as to what is happening. Essentially, we have flow coming in. The flow is coming in as a 1D flow, and little by little, it's turning into a fully viscous flow affected by the whole viscosity of the flow. And that's what we call the entrance length, or the entrance region, is this transition from flow outside to flow fully inside the system. So a little bit more description of this. So we can say that the distance from the start of the pipe where the inviscid core disappears and boundary layers merge. So this is shown by the black dotted lines. Okay, so it's the black dashed lines essentially. Shows you how the boundary layers are merging and the inviscid core flow. Now, this distance from the start of the pipe where the inviscid core sort of slowly disappears and the boundary layers merged can be written as length of E is a function of a few different things. So it's a function of diameter. So it changes with diameter. It also changes with the velocity of our flow. So if we have a different velocity, this length of the core could be different. This length of the entrance could be different. Also, it varies based on density. So if we have a different density, it could be a function of density as well. And it's also a function of viscosity. Okay, if we change our fluid from water to oil, our entrance length or our developing region will change. Okay, so there will be a difference. And if we look at this equation, we should know from our previous module how to non-dimensionalize it. So we can actually rewrite this to make it non-dimensional. So we can say that LE over D, so we're going to divide by distance on the left, is actually equal to a new function g of rho vd over mu. And you could have non-dimensionalized this equation by just using your techniques from module 5, but here it's done for yourself. This was more of an exercise for you. And so we know that the length of the entrance divided by our diameter is going to be equal to a function of Reynolds D. So depending on the Reynolds number, our length of the entrance is going to change. And now the only thing we have to do is run some experiments, because we know that the length of the entrance is affected by Reynolds. You can do different experiments at different Reynolds and get an equation for your function. And it turns out that the function for laminar flow, so if we have laminar flow coming in, so Reynolds number that's laminar, we get that from experimentation, LE over D is approximately equal to 0.06 Reynolds D. So essentially our function G is actually 0.06 multiplied by Reynolds. Okay, so this has to be used for Reynolds is less than 2,300. Okay, and that means that if we have a Reynolds number of 2,000, or let's say less than or equal to 2,300. So if we have a Reynolds number of 2,300, which would be our limit for what is considered laminar flow, our max entrance length would be equal to the following. We can actually plug in 2,300 multiplied by 0.06, and we would get that LE is equal to 138 times the diameter. So if we have a diameter of 1 meter, then we know our length of the entrance is going to be 138 meters. Okay, so it's actually a pretty slow process. Okay, we see that the boundary layer grows very slowly. It grows at 138 times the diameter. So it's actually a pretty long process. Now, for turbulent flow, which we'll address later, so for turbulent flow, we actually have our boundary layer, or BL, okay, that's boundary layer, grows faster. And it grows faster because there's more chaos and it's easier for it to grow. So that means that LE is shorter, or the length of the entrance is shorter. And this length of the entrance is now used with a new function above 2,300, which is equal approximately to 1.6 times Reynolds to the power of 1/4. Okay, and this is usually, the equation is, so I'll put this in red just so we know that it's a governing equation, and this too. And this is usually for Reynolds is less than 10 to the 7. Okay, above 10 to the 7, it becomes less interesting to look at this, as they can't really figure out a consistent equation that will give you the length of the entrance once you have fully developed flow, essentially. Okay, so we've been able to figure out how to find the length of the entrance based on the diameter and based on the Reynolds number of our equation. And we used a combination of Module 5, Module 3, and Module 4 to understand what is happening. Okay, so we're going to take a break here, and we're going to come back in video 2 to discuss head loss and the friction factor applied to pipe flow, and then we'll go into fully developed laminar flow and looking at an analysis of fully developed laminar flow with some examples.